Alrighty, guys, Mr. Dominguez back with another video, and this time I'm going to show you guys how to write ionic formulas with different kinds of cations and anions, whether it be monoatomic, polyatomic, or transitional metals. All right, so let's start with the easy ones first, which is the monoatomic. Now, we've talked about this before, but I always think it's good to remind you guys about how we write these things. So first and foremost, let's take a real simple one. Let's take a monoatomic ion, meaning that it just means one, right? One element in particular. So we have sodium, which has an oxidation number of +1. Remembering that the reason it has an oxidation number of +1 is that it gives up its one electron and becomes a positive cation. Okay. Now we're going to match this up with an anion, which is -2. Once again, meaning that it has gained 2 electrons. Now, due to intramolecular forces, these two are going to be attracted to one another and then be bound together in a ionic compound. Now, so we have to write the formula down for this. The way that we would do that is I always tell kids, best way to do this is to write, the easiest way, right, is to write the cation and also the anion together like that. Circle the number that is in front of the charge. In this case, it would be the 2, so I'm going to circle that one. And if there is no number, circle nothing there. Okay. And what we're going to do is we're going to crisscross these numbers and put them down below, behind each of the elements in the compound. So we're going to bring a 2 down here. So write the 2 right there. And since there's no number to bring down from sodium, now I'm going to bring it down a number. So our chemical formula for this monoatomic ion, or sorry, this ionic compound with these monoatomic ions is going to be Na2O. All right, awesome. How do we name it then? Well, when it comes to naming ionic compounds using monoatomic ions, it's actually pretty simple. So first of all, the cation name doesn't change at all, so it still stays sodium. And oxygen does change. So the way that you do this is you find the first valve, which in this case is Y. We drop everything after it. So we're going to erase all this stuff right here. And we add an I, D, E. So the name of this compound is going to be sodium oxide. Pretty simple stuff, right? Now, there are some examples in which you're going to have to do a little bit more work. So let's take, for example, a compound with 2 ions. Let's say one of those ions, in this case, is going to be, let's say, calcium. Now, if you look at the oxidation number for calcium, it's 2 positive, like some of you guys. All right. And we're going to match it up with our good old friend, oxygen, once again, because we like oxygen. And more specifically, because like some of you guys, it's a little too negative. Ah, there's a dad joke for you guys. All right. So we got these two little things right there. All right. Now, remembering that this right here is our cation. And the reason we know it's a cation is because it's positive. And this right here is our anion. And the reason we know that is because it's negative. Now we're going to do the same thing we did before. We're going to write down our two elements down below, calcium and oxygen. And we're going to circle our two numbers in front of our signs. So we have 2 and 2. We're going to bring both of those down. 2 comes down here and 2 comes down here. Okay. So we're going to write a 2 right here and a 2 right there. Now, most of you guys are probably sitting to yourself, Mr. Dominguez, that don't look right. And you would be 100% correct in assuming that it does not look right. And the reason is because when we write ionic formulas, they are written as an empirical formula. Now, what makes empirical formulas different than, say, molecular formulas is that empirical formulas are in their lowest ratio form. So, I misspelled that too. So, what that means is that it can't be 2 to 2 because in reality, 2 to 2 is the same thing as saying 1 to 1. So, we can't write it as Ca2O2. Instead, we write it in its empirical form with its lowest ratio. So, we write it as CaO, right? And the name of this, just like we talked about before, is calcium. Remembering that our cation doesn't change, but our anion does. So it's not oxygen, it's oxide. So the name of this new formula that we made is calcium oxide. Easy stuff, not too bad. Good job so far. All right. Well, like my favorite celebrity chef used to say, let's going to kick it up a notch. Bam. All right. So now we're going to switch over to what we call polyatomic ions. Pretty much the same thing, just with a little bit of a different degree of difficulty. So for those who know what polyatomic ions, those are ions that have more than one element associated with them, typically held together through covalent bonds, which give them sometimes a charge. And we talk about formal charges and all that stuff right now, but let's skip over that. Let's get to the easy stuff first. Okay. So a couple examples of anions that are polyatomics. Now, I'm not going to make you memorize all of these in my class if you're in my class, if you're just watching the video for a little bit of help. But some of these you just use so much, you just kind of you get used to them and you just kind of memorize what they are. You can always look them up. I'll give you a sheet or something like that, or you can look it up online. But some of the more common ones that you'll see in my class will be like a negative one, like nitrate, NO3, and it's negative by one. Should probably put the name next to it, huh? Nitrate. And like I said, it is an anion because it is negative and it's negative by one. Other examples that we'd have would be something like, well, I don't know, sulfate. Why not? SO4, 2 negative, spell that, sulfate. And then maybe every once in a while, you might see this one. You might recognize this one from biology. PO4, and this one's going to be 3 negative. And that's known as phosphate, an ATP. Now, I'm going to add one more just because it's my first personal favorite to say. I just like saying it because it's fun. So we got manganese and we got oxygen, which gives us permanganate. Love saying it. It's my favorite. Makes a pretty like purple color. Manganate. All right. Oh, I spelled it wrong. There we go. That's better. All right. Now, those are all the anions that you might see. I mean, there's a lot more than just this. Obviously, there's perchlorate, there's iodine, there's just a bunch of them. Okay. But we're only going to focus on these. It just makes it a little bit easier for us. Now, ideally, though, not ideally. There's only really one cation that you'll have to memorize because you'll see it a lot. And that's this guy right here. So we got a little bit of nitrogen with 4 hydrogens, and it gives us a positive charge by one. This is known as ammonium. All right. Ammonium is the only cation you're going to see that's positive. It's polyatomic. So for our class, that's all you have to worry about. Okay. Now let's get to the crux or what we're actually trying to do in this lesson. And that's how to write chemical formulas or specifically ionic formulas using polyatomic ions. So let's take, for example, a regular old monoatomic ion. Let's say, I don't know, magnesium, right? So we got Mg. And if you remember, the oxidation number for magnesium is 2 positive. Now we can get that from our periodic table by simply seeing how many valence electrons it has and how many it's going to lose. All right. And we're going to match this sucker up with, I don't know, let's say nitrate, NO3, and it's negative by one. Now, I know what some of you guys are saying, Mr. Dominguez, I can't find nitrate anywhere on the periodic table. That's because it's not on there. Nitrogen's on there and oxygen's on there, but nitrate as a whole, heck no, not on there anywhere. So this is what I'm telling you that some of these you're just going to have to kind of know. Knowing that nitrate is negative by one, right, is a good start. All right, now, luckily for you guys, the rest of this is actually the same way that we've been doing before. So I'll write down my cation, magnesium, and then I'll write my anion, nitrate, leaving the charge behind, right? Now, just like before, I'm going to circle the numbers in front of the ions. If there's nothing there, I'm going to circle nothing there. And I'm going to crisscross applesauce these suckers and bring them all the way down behind. Now, knowing that there's no number behind nitrate, or sorry, there's no number in front of a number in front, a number for nitrate, there's nothing for me to bring down behind magnesium. Some of you guys are going to bring the number down for magnesium behind nitrate, and you're going to put it like this. All right. Now I have to know that this too applies to this whole polyatomic. So the way we show that in chemistry is we put a parentheses, no different than you would in math, except we don't put the 2 in front, we put the 2 behind just like that. All right. And there's our chemical formula for magnesium and nitrate. Now, what about naming it? Well, luckily for you, naming these guys It's actually pretty simple. The names don't change at all. So the name of this guy is literally going to be magnesium nitrate, just like that. Easy peasy, lemon squeezy. Super simple. Not too hard. I would say of all the ones that we do, polyatomic ions can sometimes be the most challenging for students to use. And it's only because you have to memorize some of this stuff. But like I said, because you see them so often, oftentimes it's just simple attrition, you'll just memorize them. All right. So let's go to another one. Last but not leastly, let's talk about how we write chemical formulas for transition metals or transitional metals, sorry. Okay. So this one actually is, I would say, even easier than the monoatomic because they literally tell you. So transitional metals, some of them, you won't know how many valence electrons. So we have to literally tell you how many it has. So as a perfect example of that, I would say something like ones that we'll see oftentimes in this class would be like silver one. And the way we write this is we literally write silver. And then as a Roman numeral, we put the number one just like that in parentheses, letting me know this particular silver has one valence electron and an oxidation number of +1. Now, because these are all metals, they're all going to be cations, so they're all going to be positively charged. Other ones that you might see would be something like lead. We're actually going to see two different types of lead. One of them will be lead 2, or in some cases, lead 4. All right. So knowing that, let's take one of these where we'll even make it a little bit challenging. Let's say we're going to take a polyatomic and one of these transitional metals. So let's say we have something like, oh, I don't know, lead 4 and sulfate. Why not? So we have lead 4, peanut butter, Pb, and if this is lead 4, that means it's going to be positively charged by 4, just like that. Right? And sulfate, which we know because it's a polyatomic and we just memorize these things, is going to be negative by 2. Okay. Now, when we go to write this chemical formula, all we're simply going to do is we're going to write the elements down below, just like we've been doing before. So we got lead and we have sulfate. Write them down just like this, giving ourselves a little bit of space because something's going to happen here in a bit. Nothing serious. You guys can relax. We're going to circle our 2. We're going to circle our 4. And we're going to crisscross applesauce these guys. Okay. So the 2 would come down here, just like that. And a 4 would go behind the sulfate. Now, remembering that a parenthesis has to go around the polyatomic because we want it to apply to the whole thing, just like that. Now, I know what some of you guys are saying. Mr. Dominguez, you're probably throwing stuff at your screen, yelling at YouTube and saying, hey, that is not an empirical formula. That is not its lowest ratio. And you would be 100% correct because we can reduce 2 and 4, right? So, since we can reduce this, we know that 2 goes into 4 2 times and 2 goes into 2 1 time. We can simply take out the 2. Let's erase this guy. And we can take out this 4. And instead of having a 4, we can have a 2. Oh, come on, click on it. There we go. We're going to put the 2 right back there, just like that. So our chemical formula for this compound is Pb, and then we have SO4, and there's 2 of them, just like that. Still using the same method that we learned way back at the beginning of this lesson. So what about the name? Well, just like we did before, the name has to actually show how many valence electrons or what this transition metal actually is. So in this case, we have lead 4, right? So we're going to write that lead 4, and we're going to write this in Roman numerals, remembering your Rocky movies. Rocky 4, Adrian lives. Right, so lead 4, and after that, because we have a polyatomic, the name doesn't change. We're going to keep it exactly the same. We're going to say lead 4 sulfate, just like that. The next time you're in the lab, you don't have to sound like a goofball. You can actually tell me what it is instead of saying PbSO4. You can say it's Mr. Dominguez, it's lead 4 sulfate. All right, ladies and gentlemen, I hope that helps. That was 3 different types of of ions that you can form and how to write the formulas, starting with monoatomic, polyatomic, and finally transition metals. All right, if there's any questions, please let me know. Take care, everyone.